the lab was doing a lot of really cool virology work. And at that point, I hadn't thought a lot about viruses and infectious diseases. Keep in mind, this was 2018. So everyone was just sort of like, yeah, viruses, they're like pretty scary, pretty important. Our lab did a lot of like Ebola, sort of West African tropical diseases research. But I was thinking like, oh, there are a lot of other just more ubiquitous viruses like flu that could cause much more widespread infection. And then 2 years later, another virus, COVID, did cause widespread infection. So
Hey there, I'm Luca Fusar-Bassini. I'm a PhD student in computational biology at EPFL in Switzerland, and you're listening to A Biotech Futurist. The Biotech Futurist aims to foster deep understanding and discussion about exciting hot topics in biotech, but I want to say from the beginning that it is by no means rigorous in teaching the subject. And for the sake of outreach, sometimes we need generalizations that, of course, simplify the reality of the science behind what we're discussing. But I can say that my guests and I do our best to be clear and to go in depth. You can imagine to be out with me and my expert guest for a friendly conversation to get a general understanding and more curiosity, having fun as much as I've had recording this podcast. This podcast has no sponsors and any reference is not meant to support any commercial activity. This podcast is a solo effort, so if you wish to support me, I'd be grateful if you followed the Biotech Futurist on Spotify, Apple Podcasts, YouTube, Instagram or your top podcasting platform and share it with your friends. With that said, I am excited to move on to today's conversation at the Biotech Futurist. Today, I have a pleasure to discuss state-of-the-art diagnostic for infectious diseases with my friend Ben Zhang. Ben is a medical student at Harvard Medical School. He has worked in the Sabeti lab on CRISPR-based diagnostic for flu and COVID, receiving the Thomas Hoopes Prize for his outstanding work. And Ben defines himself as passionate about youth development, and I would add also sports. Ben, can you tell us about you, your scientific journey so far, and your dreams and plans for the future, please?
yeah, thank you so much, Luca, and thank you so much for having me on this podcast. I'm really excited to share some of my interests and some of my work and some of like the future directions that I see going with this. So I'm Ben. I am a first-year medical student at Harvard Medical School. I was born in China, moved to New Zealand when I was 6, so I grew up in New Zealand, and then came to America for university, where I did my undergraduate studies, also at Harvard, studying molecular and cellular biology. And during my undergraduate studies, I worked in the Sabeti lab for all 4 years of undergraduate work. And it was really sort of just by luck that I stumbled upon the lab. I connected through another professor, and I saw that the lab was doing a lot of really cool virology work. And at that point, I hadn't thought a lot about viruses and infectious diseases. Keep in mind, this was 2018. So everyone was just sort of like, yeah, viruses, they're like pretty scary, pretty important. Our lab did a lot of like Ebola, sort of West African tropical diseases research. But I was thinking like, oh, there are a lot of other just more ubiquitous viruses like flu that could cause much more widespread infection. And then 2 years later, another virus, COVID, did cause widespread infection. So just thinking about diagnostics and how to be able to detect these viruses sort of really captured my scientific interest, and using this new technology platform that we developed in the lab to create these really sensitive, really simplified diagnostics. And I think for my medical journey, so I did all this infectious disease stuff, but I actually don't think I want to go into like infectious disease doctor. I'm actually really interested in surgery, specifically like orthopedic surgery maybe, or just other areas or general surgery, cardiothoracic. I'm still exploring my interest there. But I hope definitely with my career, I know a lot of surgeons are very busy all the time, but I hope to be able to at least embed in some research into my surgical career in the future as well.
Wonderful topics for next podcast episode, I guess. So yeah, let's start dealing with today's topic, which is indeed the need for low-cost, easy-to-use, scalable, and sensitive diagnostics for infectious diseases. I mean, we are all familiar now with COVID at home tests, which were fundamental for how the pandemic worked out. But home tests are based on antigens and not nucleic acids. This means that they are less sensitive compared to the swab tests followed by PCR that most of us have done in the course of the pandemic at their local drugstore or hospital and whatever. So Ben's lab, I mean, the Sabeti lab where Ben worked, has been doing a lot to improve our capability to make sensitive diagnostics that can be deployed everywhere with low cost, easy for everyone. I think that facilitating easier, more widespread screening to contain epidemic outbreaks is nowadays an urgency more than ever, and we know it by experience. So I'd say that ideally one wants to make it as easy as measuring your temperature or blood pressure to diagnose an infectious disease. And possibly we'd be happy to monitor many diseases at once. So Ben, can you introduce us to what the Sabeti lab has been doing and what, in your opinion, would the pandemic have done to us in case we would have at these diagnostics in early days of COVID pandemic? I mean, this work is very recent, so even if proof of concept data were starting to be available when the pandemic struck, most of the data came after the pandemic and became very clear the importance of everything just after the pandemic has started. So, to you.
Yeah, I think, right, like I can imagine that if we had all of these diagnostics up and running and already developed, then the magic sort of this platform is that as soon as a new virus emerges and as soon as we have some like genome sequencing information, we're able to create these probes and these guides and design the assays in a really quick turnaround, probably in about 2 weeks time, and maybe give another half a week or so of testing, and then they're ready to be deployed and ready to be able to be used on patient samples like saliva, especially for respiratory viruses, or even blood samples, urine samples. These are all modalities of detection that have been validated. And just right at the beginning of the pandemic, we had the whole thing about like people were developing qPCR tests. These are the traditional tests that we get in a lab, and they just take so long to develop and they take so long to read out, and the reagents were limiting. So I think just on a general level, if we had more diagnostics in the early days of COVID, then we're better able to like see who has the infection and who doesn't have the infection. And that's going to be really important in terms of quarantine, in terms of limiting spread, and in terms of understanding the epidemiology of the virus, and not propagating it on a pandemic scale.
Mm-hmm. And also the human factor is important here. I mean, if we had home tests soon, then that would have helped, because yeah, qPCR tests are reliable, they are great, but they need a lot of personnel to be done, and not only time. So developing home tests that people can routinely take, that would surely help for many diseases. What do you say?
Mm-hmm. Yeah, completely agree there.
So maybe we can start from the beginning. What is SHERLOCK? Great name choice from the Sabeti lab. And what is CRISPR-based diagnostics in general?
Yeah, I think we can start with CRISPR-based diagnostics in general. So CRISPR, as people may know, is started off being this like gene editing software, right? Like a lot of you have a guide and you have your DNA, RNA, and then the point is that, I can use this guide to like sort of cut out a section of the DNA and just knock it out. CRISPR knockouts, they're very useful in gene editing terms. Jennifer Doudna and Feng Zhang, their labs discovered these orthologs that are Cas12 and Cas13 that instead of just being able to edit the genes, that when the guides recognize the viral sequences in this case, or any other DNA or RNA sequences, it doesn't just cut that sequence, but it cuts any other free-floating short nucleotides as well. And that's really useful because the whole sort of paradigm of detection, right, is just if I see something, I want to be able to produce some sort of signal, right? CRISPR-Cas9 doesn't do this very well because it just sort of cuts the thing that I'm seeing and I'm not creating any signal. But Cas12 and Cas13 does this really well because when I sense my virus genome, it's able to do other stuff like cut nucleotides around it, and then we can do some really smart engineering things like with fluorescence or with lateral flow, with like the color strip readouts, that you're able to visualize when this happens. And when you're able to visualize the presence of some genomic material, you're able to create viral diagnostics. And SHERLOCK sort of builds upon this principle, and it's using Cas13, also coupled with an isothermal amplification method called RPA. So you can just think about RPA as like PCR, but you don't have to change the temperature.
So in very basic terms, amplifying nucleic acids without changing temperature. Very, very basic terms.
Yeah, exactly. Yeah. Amplifying the nucleic acid without changing. And why would we not want to change the temperature? Well, because it's just easier, right, to do. With PCR, you sort of need a thermocycler to like change the temperature to the specific steps. But with RPA, you can just put it in a 37 degree. Well, ideally it's 41 degree, but it can actually work pretty well at 37 degrees, which means you can sort of use body heat to catalyze the reaction. This is sort of potentially down the line field deployable applications, but yeah, and it uses the same mechanism, right? We have guides that we design specifically complementary to the RNA sequence of the virus. And then so that can detect the virus. And then the amplification step, we do reverse transcriptase RPA. So it kind of, you can't really amplify RNA. So you have to reverse transcribe it back to DNA, amplify it. And then you have a T7 transcription step that turns this amplified DNA back into RNA for Cas13 to detect.
Wonderful. So to sum up, by forgetting for a moment about the amplification step, the key idea here is that there are CRISPR-related enzymes, which you correctly called orthologs, and maybe you can define what orthologs are briefly.
Yeah, they're just other types of Cas enzymes. So they're just like of the same family of enzymes that do different stuff.
Sure, but you can find in the same genome and probably had a common protein ancestor somewhere in the past. So these CRISPR, Cas orthologs are capable of cutting some external oligonucleotide when they are triggered by base pairing their guide with cellular DNA. So they can reveal if there is a virus because they base pair with that virus, with some portion of that virus DNA, and they start cleaving some other oligonucleotide. But how can we reveal the cleavage of that other oligonucleotide? Can you explain deeper?
Yeah, so by cleaving these other oligonucleotides, we can have we can design our specific reporters with like a fluorescence on one end and then a quencher on the other end. So when the oligonucleotide little reporters are intact, then the quencher sort of absorbs all the fluorescence of the reporter and we don't get any fluorescence. But when we do have Cas13 activity that goes and cuts these reporters, then the quencher is now separated, right, from the fluorescence molecules. So they're not just within like a few nanometers, microns of each other. And then now these fluorescence reporters can fluoresce and then picked up by a plate reader.
So going back to our initial goal to develop a scalable, quick assay that can be deployed everywhere and by everyone. What you've described so far needs a spectropluorimeter, which is an instrument that is capable to read and quantify fluorescence to detect this with collateral activity of the Cas enzyme on the probes that reveals the detection of a nucleic acid that is indicative, for instance, of a virus. How did the Sabeti lab approach the issue of having a spectropluorimeter, which maybe is something complicated that not everyone can have at home or in developing countries with lateral flow strips? Can you describe this for us, please?
Yeah, exactly. So part of our effort to sort of make it more field deployable, make it more cheap and scalable and less equipment intensive, so we still have reporters. We need to somehow think about ways that we can show oligonucleotides being cleaved. And one way that you could do that is by using biotinylated reporters. So essentially you have these two lines on these really stock pre-made lateral flow strips that sort of just, you can think about, there's two different molecules on each end. When you wash it through and there's nothing, then you get attachment of one of the ends to the line, which has antibodies specific for one of the ends. And when it's cleaved, this behavior acts differently because you have all your sort of probes bound to the first line. But when you cut them, then you have probes bound both to the first line and the second line. And that's sort of the key modality there. And then there is some really specific calibrations that you have to do, because obviously we're sort of not using the lateral flow strips as they're intended, because we're doing sort of like a cleavage assay, whereas most of these lateral flow strips are sort of doing like an antibody recognition assay. So there's a little bit of tweaking there, but the general concept is still like, how can we just attach something to these oligonucleotides to be able to determine when are they cleaved versus when they're not.
Gotcha. One question that comes up easily after saying this is, does this take time compared to spectropolarimeter detection? And in case it takes longer, how longer does it take?
So it takes about the same time. So how this works is that the Cas reaction usually takes about 1.5 hours to 3 hours before you're able to get this like really nice cleavage at 37 degrees. Essentially in a plate reader, what that would look like is that you would set up the reaction and then you would have it basically measure fluorescence every 5 minutes for 1.5 hours to 3 hours, and then you get a really nice curve of fluorescence. And how it works in lateral flow is that we would just incubate the same reaction for 1.5 hours or 3 hours, and then afterwards take it out and then put it on the strip, and the strip readout is like 5 minutes. So the time scales are about the same. And of course, that is something that we could work to improve as well, because you might not have 1.5 hours or 3 hours at home to be like waiting to see the results of the lateral flow strip, or like to incubate your little sample. So being able to do that more rapidly would be a big plus in the future as well.
Yeah, and what are the strategies that you envision as feasible to do so?
I think just thinking about different analogs of Cas13 that's able to just do this reaction quicker, right? Like enzymes that are more that have higher nuclease activity once recognition occurs. Again, it's going to be an issue of like on target versus off, right? It's like collateral cleavage specific to recognition versus just background collateral cleavage. And part of the lab that my postdoc is not in the Sabeti lab, so I used to work with a postdoc in the Sabeti lab. Now he's a professor at Princeton. His lab is looking at sort of developing Cas13 engineering to get Cas13 to be quicker, be more specific, and have a lot higher nuclease activity. So he's doing exciting research there.
Yeah, nature with its enzymes is always the master in telling us how to make things faster and better. So for sure, forcing evolution in some sense for these enzymes is a key strategy to improve speed and efficiency. I think that you've also been working on something like multiplexing and doing multiple reactions in a single pot, so to detect multiple viral species or multiple nucleic acids for the same virus, I don't know, in the single reaction. Can you tell us more about this and how you can really see multiple viruses within a single reaction?
Yeah, and it sort of works now we just have duplex, that's where we're at so far, and it depends on, right, we have our Cas13 and Cas12 enzymes, and the good thing is that they work separately on different things. So Cas13 recognizes RNA, and then it cleaves RNA oligonucleotides, whereas Cas12 recognizes DNA and cleaves DNA oligonucleotides. So based on this principle, we can have our two different viruses, right? Two different RNA viruses, and then we could do RT-RPA amplification. And then once we do that, so we get a lot of these DNA now, right, of both viruses. But based on the primers that we use, only the one that will be detected by Cas13 will have this T7 transcription little promoter in front of it. So then we could do T7 transcription on that one, and then it'll make the RNA version of the Cas13 one that it's trying to detect. So then Cas13 will detect the RNA, Cas12 will detect the DNA, and then so in that same reaction, we can have both DNA oligonucleotide reporters and RNA oligonucleotide reporters, and then based on what's present, the Cas12 and Cas13 will cleave each of these respectively.
So the key idea here is to use 2 different nucleic acids and 2 different enzymes, each of them only detecting one of the 2 nucleic acids. So yeah, it would be interesting to develop some artificial chemistry for nucleic acids and correspondent enzyme to make these even more multiplexable than duplexes maybe.
Yeah, exactly.
Where do you see this technology and its related improvements for this technology in the real world in 5, 10 or 25 years?
Yeah, I mean, I think the duplex stuff is really something that's exciting that's coming along, but it's sort of something that's just like fun to have and sort of collapses everything. I think the real strength of these assays will be in the lateral flow readout and the mass appeal, because it's just 10 times cheaper than qPCR per test when you actually produce it in scale, because of the ability to just freeze dry our ingredients, sort of like the at-home rapid antigen test that you've been getting, right? You can just get like a little package of stuff, you'll rehydrate it, you'll put your own sample in, and you'll leave it for however long, and then you'll read it out. That is the potential of where this technology is heading, and I think there's obviously a lot of optimizations, a lot of engineering that needs to go into these like chemical reactions to allow them to do that. But even in the lab, as we're setting them up, it's like this is the possibility that we're working towards.
Sure. One of the exciting technologies related to SHERLOCK that the Sabeti lab has been working on, especially for SARS-CoV-2, is SHINE. As the paper's title says, SHINE stands for Streamline Inactivation, Amplification, and Cas13-based detection, and there's a great example for SARS-CoV-2. So this is a single step. It works on unextracted samples. It's based on techniques that reduce the contamination risk, and it can be interpreted by smartphone app. First of all, I wanted to ask what is an unextracted sample and why it is challenging to use an unextracted sample, but at the same time fundamental to do so to make things better in some sense.
Yeah, well, an unextracted sample really is just saliva, right? The saliva as input. The reason that you're able to use a rapid antigen test and use saliva and not have to think about extraction is because a rapid antigen test detects proteins or like epitopes, right? Based on antibody binding. So it's like already there in the sample itself. Whereas in nucleic acid tests, the nucleic acids are not just floating around in the sample, right? They're in the cell, they're in the viruses that we're trying to detect, right? A lot of the times they're actually in the cells that we're trying to detect. And so extraction, why qPCR still cannot detect unextracted samples, is because you first need to go in and take out all the RNA.
So to sum this up, Ben and I have been extracting a lot of nucleic acids from stupid cells that have membranes. Now we want to do something that doesn't need to do this boring step of extraction, something that people can use without doing many experiments as we do in the lab.
Yeah, and exactly. It's actually really simple, and I think there could be more elegant ways as we develop this, but so far we've just been using this like commercially made thing called Intact Genomics, makes this a viral lysis buffer that basically just lyse the virus particles and then like releases all of the nucleases. Obviously that's not ideal because then you have RNA, you need to put in RNase inhibitors to not degrade your sample, but still there's just a lot of gunky stuff floating around that could be impacting the reaction. So we need to think about ways also to keep the quality of the sample high as well when we do that.
Yeah, the difficulty and the reason why in molecular biology we typically do many reactions separately to achieve a final goal is that different enzymes need different pH, temperature, salts, inhibitors, and whatever. So we really have to purify from time to time our solutions. And if we want to make an assay that works easier with just a single tube, of course we have to somehow trade some benefits of a given enzyme for benefits of another enzyme, and this is for sure difficult and needs a lot of testing. So how were your group, the Sabeti group, able to develop SHINE to make it as simple as possible in an extracted sample with multiple enzyme reactivities?
Yeah, I think just a lot of testing, a lot of testing, and all of this was happening over COVID, so it was tough with So I wasn't actually in the country, and I wasn't part of the initial development of SHINE, though I was sort of like brainstorming ideas and seeing the results come in of people actually doing it on the ground in live, and there's just a lot of testing, a lot of experiments not working, and thinking about the different interactions, because yeah, there are trade-offs, right? It's not as sensitive as SHERLOCK, but you do get that nice reduction of contamination risk, which is really cool. But overall, the enzymes work less well because you're sort of just pulling them all together, and you're like, I'm just finding an intermediate range where each thing works well enough to give me some detection, and it works pretty good. But ideally, there are ways that we can make it work better in the future.
And what enzymes and reagents do you have in a SHINE tube?
Yeah, so we have essentially all the things that you have in a two-step SHERLOCK with RPA and detection, but now it's all together. And the difference is that we're adding in RNase H, and that's something that a grad student in our lab, John, discovered. And so this is where the empirical thinking comes in, right? Where SHINE is not working well in one part format, and we were thinking like, what is happening? And then one hypothesis is that it has something to do with the RPA, because amplification and detection are happening at the same time. There could be things it's sort of like you cannot detect something that is actively amplifying, right? And so RNase H is an endonuclease that comes in and sort of cleaves DNA RNA complexes that allows us to be able to detect things a lot clearer in solution. So that's one specific improvement that we made, and then one extra reagent that we added there.
Yeah, that's super interesting. When I read the paper, I was surprised because it's not a typical enzyme that you expect to be inside of such a mix compared to what we do in the lab. So yeah, that's great, and also inspiring to just mix up enzymes that make rational things, but you wouldn't expect typically. How do you concretely evaluate the sensitivity of the SHINE assay? I mean, you said that maybe SHERLOCK is still the gold standard, but SHINE is very performant, so sensitivity is the best measure of performance in these assays. And how can you really take a tube and say, well, this assay is sensitive, and if I add this enzyme, if I change this parameter, then it is less or more sensitive?
Yeah, we do a limit of detection assay. So we order synthetic sequences, probably like 500 nucleotides around the exact site of our detection. And then so with our DNA samples, we do that. So when you buy the G block from IDT DNA, they tell you how much, you dilute it to the amount so you know the exact concentration. And then so for RNA detection, we'll transcribe the DNA G blocks ourselves and get in vitro transcribed RNA, and then we'll quantify it on a nanodrop to know exactly the concentration of RNA, and then we'll do a limit of detection. We'll do like 100,000 copies per microliter, 10,000 copies, 1,000 copies per microliter, 100 copies per microliter, 10, 1 copy per microliter, and then we'll see at which point does it stop detecting the RNA in the sample, and that's interpreted as the sensitivity. Yeah.
That makes absolutely sense. So after SHINE, the Sabeti group also developed SHINE version number 2. I don't know how to say this, but one of the key ingredients in SHINE second version is that there are no heating steps, but body heat is enough. And this is relevant for sure for what we were saying, that you want to make this assay feel deployable, whoever can use it, and less equipment possible. It also eliminates the need for cold storage of reagents, and it enables visual discrimination of COVID variants. Ben, can you tell us more about the innovation behind the design of SHINE second version for SARS-CoV-2 specifically, and for its variants of concern, such as the variants of Omicron?
Yeah. So Shine version 2, right? The big banner is that like you don't need heating steps, body heat is enough. Well, it's sort of just carrying on from Shine V1, right? Because before we were sort of just incubating things at 37 degrees Celsius, whereas now we're just putting it into your armpit, which if you hold it tight enough is about 36, 37 degrees Celsius. So it's but the more exciting part is the lyophilization. That's what we call it in the paper. And lyophilization is basically just freeze drying. So you would make up your master mix, detection master mix, and then you would dunk it in liquid nitrogen and put it under a vacuum. And then through doing so, you let the water sublimate, essentially, leaving only the everything dissolved in the water behind, but it's dehydrated, so then it's going to be shelf stable. You can store it for about a week at room temperature, or many weeks. I think we tested up to like 3 weeks, just in a fridge, which is really nice because that means you can keep it on ice for a long time, or like in dry ice, right? You can keep it really fresh. This is like resource constrained settings, because some of the reagents in Shine and in SHERLOCK actually need to be kept at -80 in a storage solution format. So being able to keep everything just at fridge temperature or even at room temperature for up to a week is going to be really important in terms of getting these assays out into the field in resource limited settings. And I guess the design of Shine for COVID and its variants of concern. So the variants of concern is really just showing that we're able to change assays and change the sequences because it's just dependent on CRISPR RNA sensing the specific sequence, right? So as COVID variants came up, we're actually able to change the sequences in real time to discern and differentiate between the different strains, just to show that that is something that's an advantage of Shine as well.
Yeah, and that can really be helpful to follow and track variants over the globe as they emerge. So a test that not only understands if you have COVID, but also what variants you have, can help then authorities to track how variants are spreading around the globe. Yeah. I also wanted to ask what different features an ideal assay has, and what do you think that Sabeti Lab and other people in this field will try to do in the next few years to make it even better and to make it a commercial assay that everyone basically uses?
Yeah, I think an ideal viral diagnostics has a few certain aspects, and they're pretty intuitive if you think about it, right? You want something that's highly sensitive, that can detect very low copy numbers, right? So sensitivity and specificity, obviously our classic diagnostic paradigm, right? You want something that's specific as well. Like you want to be able to detect the thing that you have, right? And that's the benefit of qPCR and nucleic acid tests, is that like they're pretty specific. It's unlikely to get something else and then get a false positive and say, oh, that is this virus, because it's based on nucleic acid sensing instead of just random protein binding as well. And the next thing is obviously going to be cost. So cost per assay, cost of equipment, cost of setup of diagnostic capabilities. And then what I always think about is like how deployable is it, right? Again, the realistics of logistics and everything like that. Those are the key important things that you have to think about when developing a biodiagnostic.
That's inspiring. And maybe now we can shift topic just a bit, but I know that the Sabeti group has been working on a lot of machine learning to make these viral diagnostics even more powerful, especially with a paper that designed assays that keep into account viral variation. Indeed, as we know well for COVID, a virus is not just a given genome, but viruses evolve pretty quickly, so they are quite variable, and especially some regions of a virus can change rapidly, and we want an assay that is able to deal with that variation to detect viruses still sensitively. So the group designed a machine learning framework for quantitative prediction of an enzyme activity of a diagnostic first. To do so, they generated a dataset with a library of target sequences and complementary guide RNAs for Cas13a, as Ben was describing. Here, targets have mismatches to keep into account indeed the viral variants. And they used a fluorescence measure to find a readout that could quantify and associate with sequence features the activity of detection of the diagnostics based on CRISPR-Cas13a. So, Ben, what is Carmen and how does it work to make screening of 19,000 plus guide target pairs feasible in a reasonable amount of time and not hundreds of years?
Yeah, so Carmen was the other project that my postdoc, now professor at Princeton, was working on, his sort of other project. So whereas SHINE and SHERLOCK is really sort of thinking about single sample patient, right, direct deployment, Carmen is really thought about in ways of surveillance and just being able to test tens of thousands of samples in parallel and like massively multiplex everything. And you do this through, there is the Carmen paper that you could read about later as well. It's actually really interesting, is that you make these little nano drops basically. So you have different pools and you amplify all of them. And then you tag each of these pools fluorescently. And then, so you have like guides, which are pooled and tagged, and then you have targets that are pooled and tagged. And then you put them all together, just in a tube, and then you dissolve them in different solvents. And these solvents, they kind of like don't mix. And then you put these tiny droplets, so you do little droplets, right? Just imagine they're like little ice cream, little ice cream, right? Just imagine they're little ice cream droplets, but they're like micrometers, nanometers big. And so each one has like a little drop of the CRISPR RNA and the target. And then you have them all sitting there, and they're not mixing because they're not fully viscous. And then what you do is you shake them a little bit. So then pairs of things begin mixing. And then when they mix, basically a Cas13 reaction will happen, and then you can detect that fluorescence. And you use a super, super sensitive microscope that goes in and then basically detects the fluorescence of every single one of those reactions and then aggregates them based on the tags that you put in. And then in doing so, you can then intuit out the collective, right? You can then average over all the possible, because the idea is that we have so many droplets that we're going to get every single combination, right? So just by the sheer number of droplets that we're doing, we're going to get every single combination, and then we can average over all of those combinations to get, like, for example, if you have 50 guides, 50 targets, then you can get every possible guide target pair and get their fluorescent values. And obviously, right, and then so when I heard this, I was like, oh, but then, like, aren't you also having, like, droplets of, like, CRISPR RNAs mixed with CRISPR? And they're like, yeah, there will be droplets of, like, just CRISPR RNA and CRISPR RNA and just target and target, but, like, those just, it's fine, yeah. Right, it's like we have every single combination, right? So, yeah, and exactly. And so the thing about that is that's just, like, more just, so, right, you need expensive machinery, fancy reagents, right, that's just very super high.
Okay, so now we have all this fluorescent data that indicate the activity of a given enzymatic diagnostic, and we want to model this activity for each combination of guide and target. And the idea here is to develop a classifier that says, well, this guide for this target is active, or this guide for this target is not active. So first a classifier, yes or no. Is this guide target pair active or is it not? And then also the lab developed a regression for the active guide target pairs. For people who like machine learning, the final model is a convolutional neural network, but also our models and simpler models have shown good performances. So I want to ask you, Ben, what are the inputs of this machine learning classifier and regressor and models? especially how do they use nucleotide sequences?
Yeah, exactly. So, well, you can think about it, right? Like, we're just having a lot of targets and a lot of guides. And the idea is that we're just tiling guides on a specific target, on just a sequence, and we're introducing mismatches at places. And what it's really telling, what the machine learning model is really modeling is like, how do the exact sequence, right, the ATGCs, affect or the proportion, right, or the feature space, you can think about it that way, really affect Cas13 binding, because that's something that we don't understand really well. And this is where machine learning is really powerful, is that as long as we just have a shit ton of data, we can just intuit, well, the machine learning algorithm can intuit exactly what features of the sequence and of the surrounding sequences are important in a Cas13 recognition and collateral cleavage event, because the sort of regressor that we're measuring is just the activity of the guide, right? So if we're like, this guide has, and the guide is not like a yes/no activity, it's actually a quantitative activity, right? It's like you have a fluorescence value. So you can actually get a very nice regression of like, when these features are present, this is the fluorescence value. And when these features are present, this is the fluorescence value. And obviously it's not a sort of a clear box. We don't know what features are important. We're sort of doing a deep learning method where we're just like, oh, here are this thing, right? Intuit from this, and then you're able to use this model to predict future guides. But what the model isn't able to tell you is what features are important. And that is something that we could work towards. And that was something that I had suggested, but I had no time to work on and thinking about like the exact features that might allow the model to work better.
Yeah, it would be very interesting to understand what happens under this network. How is it, let's say, thinking, and especially maybe there is some explainable machine learning tools out there that can be deployed also in these instances to find out what is important, I guess. I mean, maybe the length of a guide. Are you changing the length or base composition or whatever features? Sure. Let's take a stop here. Okay. Just because I have a sign in my record, so I can go back and track where I have to cut. Okay. Now maybe we can just go to the next topic. Yeah. Okay. So the paper shows that integrating a virus's variation into an objective function can be used to optimally design a sensitive diagnostic across viral variants, including both existing viral variants and likely emergent in the near future. What are the inputs and what are the outputs, say, given the novel coronavirus? What do you need to know, and what feature of a diagnostic you get from the model? I mean, the model designs the guides, but how does it design the guides? What are the primers, guides, whatever? What are the output of the model?
Yeah, the outputs of the model are essentially the primers, right, the guides, and it'll list them all in terms of the likely sites, and it takes into account like conservation, things like that. So yeah, basically primers, guides, and also like the location within the genome of where these primers and guides go. And the inputs are essentially all you need is just the diversity of the sequences that you want. So like as many coronavirus sequences that you can get your hands on, basically. Obviously, the more the better, that it's able to account for all the variations that you're giving it. And then another input is going to be just your thresholds, right? For example, you can choose what fraction of the sequences do you want your guide to ideally be able to target. So for example, for flu, I chose 0.95 so that my guides could have to be able to hit at least 95% of all the flu sequences that I inputted it. And then you can think about mismatches. You can allow different numbers, up to different numbers of mismatches. And then what's really cool is the differential diagnostics. So you can give it a list of targets that the guide should target, and then you can give it a second list of genomes that the guide shouldn't target. So then you can get something really specific, right? Because you want something that can detect SARS-CoV-2, but not SARS-CoV-1, right?
Specificity is really mattering.
Yeah. Exactly, right? And then because ADAPT tends to go towards the more conserved regions, you don't want to go to regions that are so conserved that it's actually conserved across different species, right? So being able to differentially target these sequences will be really important for specificity.
Sure. So I think that also using multiple guides is something that the Sabeti group explored. I mean, multiple guides together in a single assay. But in the end, the paper says that more probes together should be penalized. Why is this the case?
Yeah, well, using more probes increases your assay complexity, right? Because you just have more probes to use, and you think about your Shine reaction. If we have 2 probes, then each probe is sort of just acting on its own. You need more reagents. It's just more complicated. So we try to stick to as little probes as we can to cover the ideal formality, right? It's like why don't we have qPCR why don't we just have like 10 different qPCR guides for like one assay, right? It's just the same thing.
Simple is better for sure. Another question that comes to my mind related to this is, okay, you have variants, and let's take COVID as this example. Maybe it's the most familiar to many people. But some variants are much more common, or they are becoming much more common than others. So ideally, in the real world, you would be happy to have an assay that maybe makes a few mistakes on some rare variant, but for the great majority, or for the most destructive variants, or for the variants that are made more concerning for health risks and whatever, they are much more sensitive. So somehow waiving the importance of different variants in developing an assay. Is this something that is kept into account in this classifier?
Yeah, and I think that's something that you can play around with as well, essentially, right? Because you can the one way that you can play with it, right? You can just change the number of sequences of each variant that you give it. So instead of all the possible sequences, you might include a subset of the less important variants, and then just have more of the more important variants. And then when you use the classifier, when you get coverage, you get more of the coverage of the more important variants.
Yeah, that sounds very flexible, and indeed it's one of the reasons why this paper is so beautiful. In what other settings may designing optimally sensitive sequences that integrate sequence variation prove beneficial outside of what we've just discussed?
Yeah, I think this is just like, if you don't look at it from like applying this to Cas13 diagnostics, I think just in general it made some really great strides in terms of just like sequence recognition and thinking about viral sequence diversity and being able to recognize that. You can imagine that someone can come along and create a similar one for qPCR probes, right? Or like any other modality that then comes along that depends on nucleic acid binding. You can use a similar approach, at least with the code. Obviously, the training data, and it's just many, many, many experiments, but the code of the approach is really robust.
Another application that I read in the paper, but it's not discussed, of course, because it's very innovative and still unexplored, is to use something, broadly speaking, close to what the group has done for vaccine design. Did you have any inspiring discussion you want to share with us about this topic?
Yeah, I think it's really interesting that for vaccine design, I mean, we're in the age of mRNA vaccines now, right? So sequences, we're always thinking about sequence targeting and different things like that. I think another thing about mRNA vaccines, like, and sequence-based vaccines, is that like it has to be able to translate to something physical and real, right? It has to be able to like make the thing that you care about. Whereas with this, we're sort of in a toy simulation space of just sequences. The sequences, right? We could be targeting sequences that are actually just not even, that are conserved, that is doing something, but we don't have to know what it's doing in the virus. Whereas I think with vaccines, you have to take into account, like, what is the function of the thing that you're targeting? Does it change a lot? Is it easily accessible to antibodies that your body will produce, right? So there's a lot of different considerations there. But I think the fundamental principles of pattern recognition and diversity will be really relevant, and just being able to sort the data.
Yeah, I think that's a space where computational genomics will be very helpful and exciting in the next few years. So you just mentioned ADAPT, which is the name, but you can also Google and have a look online for this model that the Sabeti lab has been working on. The idea is to design diagnostics rapidly and at scale. And something that is clear reading the paper is the need for periodic redesign for assays. We have a living example in COVID pandemic. Also, given that we have more and more sequenced viral genomes every day. So the group designed diagnostics for 1,993 viral species known to infect vertebrates. How does ADAPT work, and what can the user do with it?
Yeah, so essentially right now, through one of our RAs called Priya, she's a software engineer. She made this all online, this nice website that basically automatically does adapt on the currently available genomes of every single virus and every single pairwise, right? So like being able to detect this and not this. So you can go on the website, it's a user interface. So ADAPT itself, when I used it, was like a command line interface where you just have to input commands yourself. But now we have this nice graphic interface where you don't even have to give the sequences. It'll scour the database for the specific species that you want. And you can be like, I want something that detects SARS-CoV-2, but not like NLE, this sort of pre-SARS-CoV-2 sequence that we have. And then you can do that. Or you could be like, really easy for my purposes, right? I want to be able to detect flu A and not flu B. And then it'll output the guides and sequences there. Yeah, so it's sort of like it's a front-end platform, right? So Cas13 researchers from all kinds of different labs around the world, and they're trying to do different assays. They can use this as a resource starting point to develop their at least guides and primers, and then they can work on their own optimizations of those.
Yeah, that's great. Thank you for explaining. Including predictions about likely evolution of viruses such as COVID is for sure interesting, because you can design tests that do not last just a few days but can still prove sensitive and accurate when the virus evolves. So in the paper, the group mentioned that they made use of something called general time reversible nucleotide substitution model, so to design probes whose activity doesn't drop over evolution of viruses. So what is that? Can you explain us some details about it?
Yeah, I think it's just predictive modeling, basically, of like, where is the likely future evolution based on past evolution, based on just machine learning analysis of nucleotide changes of this species of virus and the place in the genome. Where is it likely to go? And again, it's just exploratory stuff, right? You're not trying to get the one thing that works. It's like, it's predicting a bunch of stuff. So you might have all of these probes ready, and then when the virus does evolve, maybe one of those probes will work. So you don't have to go through the the relatively short development, but then you already have it just right on snap. For example, someone comes into Massachusetts General Hospital and you have the probe ready. You're able to test that, and you're like, wow, that is the future evolution of this virus right here.
Yeah, so that really shortens the wait time for a good diagnostics, and still it is in line with what we've discussed so far. It is developing assays that can be really ready in less than 1 month since the virus outbreaks somewhere in the world. And yeah, that's really interesting. I mean, I would be interested in seeing a simulation of this world when the Ebola or whatever pandemic struck in the last few years, if we had these technologies ongoing. So can you tell us about what the lab is doing to use ADAPT for COVID, and in general, what are the next few applications that the lab is devising for ADAPT?
Yeah, I mean, ADAPT is now just the lab's favorite tool, right? Like my postdoc, again, I mentioned my direct mentor, he starting his own lab, and his own lab members, they want to make diagnostics for like hepatitis or HPV, right? Or just any other kind of virus. You just use ADAPT. You get the probes and you make the diagnostic. You think about different multiplexing, right? Just duplex ways. And I want these 2 viruses, and I design ADAPT probes for Cas13. So ADAPT is optimized for Cas13, but I think I can see in the future that Hayden does want to do it. He can run through the simulation of doing Cas12 as well. That was sort of what I suggested. I proposed the project. We like had a few meetings about it, and then I was sort of too busy to like actually follow through. So that's something that could be in the works if he chooses. Yeah, exactly.
Congrats for everything. So we are sure that ADAPT is so beautiful, but is there any limitation you think will be addressed?
I think, right, with any model, you can think about ways of just improving the model, improving the assumptions that you're making, improving, right? That's sort of like the tech development part, which I know less about because I'm not a ML researcher. I'm sure there's work to be done there, but it worked pretty well, probably well enough for just the general variability of how well SHERLOCK works, that it gives you pretty good guides, right? And the other thing is just that you need many, for ADAPT to be powerful, you need many sequences, right? If you just have like 10 sequences, there's not going to be machine learning stuff that you do, right? You just look at it and you're like, oh, this is the guy that I'm going to do. It's not doing anything fancy there. So you
simulate the virus. You simulate the virus evolution. Maybe you can get more sequences that may be emerging in the future by some simulation, right?
Exactly, right. That's why the virus evolution stuff is so powerful. Exactly there. But from a ground truth level, right? I have 10 sequences. I can look at it myself and make some guides, right? So yeah.
That's super interesting. And Ben, what have I forgotten to ask you about the most exciting things happening at the Sabeti lab and in your own research?
I think we covered a great track. I mean, I'm in the process of writing up my thesis into a paper. So that's going to be about flu diagnostics, flu shine diagnostics specifically. So it's a pretty nice piece of work. So that's what I'm working on top of medical school. Yeah.
Best of luck with that. And thank you so much for giving me some of your great time to share with us your insights about the future of viral diagnostics, which is really, really interesting to me. Thank you again, Ben.
Yeah.
You've just listened to A Biotech Futurist, a podcast by Luca Fusar-Bassini. This is the first series, and a new episode is out every Monday. Please consider subscribing and rating the podcast on Spotify, Apple Podcast, YouTube, Instagram, or your top podcasting platform. And if you liked this episode, consider sharing it with your friends, as the growth of new podcasts relies on word of mouth. If you have any suggestions, don't hesitate to reach out to me on Instagram or Gmail at thebiotechfuturistpodcast@gmail.com. You can find the full AI-generated transcript of this episode on my website, lucafusar-bassini.com. I'll also post the links to the main papers referenced in this episode, which you can find here in the description too. Thanks for listening to A Biotech Futurist. I am looking forward to talking with you in a week.